Hi all, Tony here for Immortality. Today we're looking at the Finalspark Neuroplatform, Organoid Intelligence. Paper is from May 2, 2024. Describes the Finalspark Neuroplatform. Article reads, Open and remotely accessible neuroplatform for research in wetware computing. Wetware computing and organoid intelligence is an emerging research field at the intersection of electrophysiology and artificial intelligence. The core concept involves using living neurons to perform computations similar to how artificial neural networks are used today. However, unlike artificial neural networks, where updating digital tensors weights can modify instantly network responses, entirely new methods must be developed for neural networks using biological neurons. Discovering these methods is challenging and requires a system capable of conducting numerous experiments, ideally accessible to researchers worldwide. For this reason, we developed a hardware and software system that allows for electrophysiological experiments on an unmatched scale. The neural platform enables researchers to run experiments on neural organoids with a lifetime of even more than 100 days. So the organoids have a lifetime of 100 days, even more than 100 days. To do so, we streamline the experimental process to quickly produce new organoids, monitor action potentials 24/7, and provide electrical stimulations. We also designed a microfluidic system that allows for fully automated medium flow and change, thus reducing the disruptions by physical interventions in the incubator and ensuring stable environmental conditions. So all these things are very important. A lifetime and the life support system and the communication system. Over the past 3 years, the neural platform was utilized with over 1,000 brain organoids, enabling the collection of more than 18 terabytes of data. A dedicated application programming interface has been developed to conduct remote research directly via our Python library or using interactive compute such as Jupyter notebooks. In addition to electrophysiological operations, our API also controls pumps, digital cameras, and UV lights for molecular uncaging. This allows for the execution of complex 24/7 experiments, including closed-loop strategies for processing using the latest deep learning or reinforcement learning libraries. Furthermore, the infrastructure supports entirely remote use. Currently in 2024, the system is freely available for research purposes, and numerous research groups have begun using it for their experiments. This article outlines the system's architecture and provides specific examples of experiments and results. So, a good overview of everything that you might do in a theoretical organoid network, but at the heart of it is how well it can perform. Introduction. The recent rise in wetware computing and consequently artificial biological neural networks comes at a time when artificial neural networks are more sophisticated than ever. The latest generation of large language models, such as Llama 2 or OpenAI's GPT-4, fundamentally rely on ANNs. Recent acceleration of ANN's use in everyday life, such as in tools like ChatGPT or Complexity, combined with the explosion in complexity in an underlying neural networks architectures has had a significant impact on energy consumption. For instance, training a single LLM like GPT-3, precursor to GPT-4, approximately required 10 gigawatt hours, which is about 6,000 times the energy a European citizen uses per year. According to a recent publication, the energy consumption projected may increase faster than linearly. This is the selling point of this article, and I've heard it repeated that the brain organoids use less energy. At the same time, the human brain operates with approximately 86 billion neurons while consuming only 20 watts of power. Given these conditions, the prospect of replacing advanced neural networks running on digital computers with real biological neural networks is enticing. In addition, the substantial energy demands associated with training LLMs, the inference costs present a similarly pressing concern. This is not a concern. You wouldn't want to give up traditional neural networks. You would want to utilize both. I don't think you can have too much of it. Recent disclosures reveal that platforms like OpenAI generate over 100 billion words daily through services such as ChatGPT, as reported by Sam Altman, CEO of OpenAI. When we break down these figures, assuming an average of 1.5 tokens per word, a conservative estimate based on OpenAI's own tokenizer data, the energy footprint becomes staggering. Preliminary calculation using the Llama 65B model, precursor to Llama 2, as a reference point, suggests energy expenditures ranging from 450 to 600 billion joules per day for word generation alone. Good argument, but it's trying to find a case for building intelligence when building intelligence is its own case. You know, who cares how much energy it takes? I mean, the more energy you can produce, the better, really. While necessary for providing AI-driven insights and interactions to millions of users worldwide, this magnitude of energy use underscores the urgency for more energy-efficient computing paradigms. There is no way we're giving up traditional silicon-based computing, regardless of how much power it draws. Connecting probes to BNNs, binary neural networks, connecting probes to biological neural networks is not a new idea. In fact, the field of multi-unit electrophysiology has an established state-of-the-art, spanning easily over the past 40 years. As a result, there are already well-documented hardware and methods for performing functional electrical interfacing and microfluidics needed for nutrient delivery. Some systems are also specifically designed for brain organoids. However, their research is mostly focused on exploring brain biology for biomedical applications, mechanisms, and potential treatments of neurodegenerative diseases. The possibility of using these methods for making new computing hardware has not been extensively explored. For this reason, there is comparatively less literature on methods that can be used to reliably program those biological neural networks in order to perform specific input and output function, as this is essential for wetware computing, not for biomedical applications. To understand what we need for programming of biological neural networks, it is helpful to look at an analogous problem of advanced neural network. For advanced neural networks, the programming task involves finding the network parameters, globally denoted as S below, that minimize the difference L computed between expected output E and actual output O for given inputs. I, given the transfer function T of the advanced neural network. This can be written as the formula where f is typically a function that equals 0 when O equals E. The same equation applies to binary neural networks. However, the key difference compared to advanced neural networks include the fact that the network parameter S cannot be individually adjusted in the case of biological neural networks. You can't adjust finding network parameters because there is a limited number of neurons. And the transfer function T is both unknown and non-stationary. Therefore, alternative heuristics must be developed, for instance, based on spatiotemporal stimulation patterns. Such developments necessitate numerous electrophysiological experiments, including, for instance, complex closed-loop algorithms, where stimulation is a function of the network's prior responses. These experiments can sometimes span days or months. To facilitate long-term experiments involving a global network of research groups, we designed an open innovation platform. This platform enables researchers to remotely perform experiments on a server interfaced with our hardware. For example, our neural platform enhances the chances of discovering the above-mentioned stimulation heuristics. It should be noted that outside the field of neuroplasticity, similar open platforms were already proposed in 2023. However, to our knowledge, there are no platforms specifically dedicated to research related to biocomputing. Well, it's similar to the old mainframe computers where there was task scheduling and you had to submit your job and the job would run through a computer at a specific time, allocated time, and or you would have to book the computer and you would get an allocated time where you had 1 hour to do your experiments, and you either got your results back or it's kind of the same thing, but there is more to it. There is more of a technical challenge here. It hasn't been done before because of the technical challenges that are involved in dealing with tissue and biological systems. That this infrastructure really relies on solving that challenge. To facilitate long-term experiments involving a global network of research groups, we designed an open innovation platform. This platform enables researchers to remotely perform experiments on a server interface with our hardware. For example, our neuro platform enhances the chances of discovering the above-mentioned stimulation heuristics. It should be noted that outside of the field of neuroplasticity, similar open platforms were already proposed in 2023. However, to our knowledge, there are no platforms specifically dedicated to research related to biocomputing. 2. Biological setup. The biological material used in our platform is made of brain spheroids, also called mini-brains, brain organoids, or neurospheres, developed from human iPSC-derived neural stem cells, following the protocol of Professor Ru's lab. Based on the recent guidelines to clarify the nomenclature for defining 3D cellular models of the nervous system, we can call those brain spheroids forebrain organoids, generation of brain organoids from neural stem cells, have been already described for both mouse and human models. Our protocol is based on the following steps: expansion phase of the neural stem cells, induction of the 3D structure, differentiation steps using GDNF and BDNF, and maturation phase. The figure 1C is an image of the forebrain organoids obtained using electronic microscope. It shows that it is a compact spheroid. The average shape of forebrain organoid obtained with this protocol are spheroids of a diameter of 500 micrometers. Our experiments show that the forebrain organoids obtained can be kept alive in an orbital shaker for years, as previously demonstrated. I don't know how with immortality, right? It's about how long can you keep these organoids alive for. You don't want to be replacing the computer every 6 months or every year. These neurons can live in an organism 100 years. Now, they can only live in captivity in the lab for 6 months with the best effort is something nearing a year. That shows how little we know about the human body and how little we know about keeping cells vital for a long period of time. So we'd expect the neurons to last 300 years in a successful biological neural network. And that means that the understanding and the systems that keep these cells alive needs to be advanced. Gene expression analysis of mature forebrain organoids versus neural stem cells showed a marked upregulation of genes characteristic to neurons, oligodendrocytes, and astrocytes in forebrain organoids compared to neural stem cells. More precisely, forebrain organoids express genes typically enriched in the forebrain, such as the striatum subpallium and layer 6 of the motor cortex. Pathway enrichment analysis of forebrain organoids versus neural stem cells demonstrated activation of biological processes like synaptic activity, neuron differentiation, and neurotransmitter release. At the age of 12 weeks, forebrain organoids contain a high number of ramified neurons, and they are mature enough to be transferred to the electrophysiological measurement system. Figure 1a, in this setup, they have a life expectancy of several months, even with 24/7 experiments that include hours of electrical stimulations. This setup has a quick turnaround with occasional downtime, about 1 hour, during organoid replacements. Therefore, the platform maintains a high availability for experiments. The expansion process, the growth, the maturation phase, the size of these neurons. Look at this 3D object. What is that? It looks like a 3D object sitting on a sensor and some kind of a liquid over it. I guess that would be that's magnification. That's magnification 500 micrometers. This is the size of it. 500 micrometers is very small, so this is very, very tiny. And so here you have the medium, the layer of the medium, which is that looks like that liquid that goes over it. The electrodes underneath, the neurosphere, and some cellular circular membrane with hole. FO generation immune setup protocol used for the generation of forebrain organoids. Neural progenitors are first thawed, plated, and expanded in T25 flasks. They are then differentiated into P6 dishes on orbital shakers and finally manually placed on the MEA, on the MIA. Representative images showing various stages of forebrain organoid formation and differentiation taken at different time points. The scale bar represents 250 micrometers. See, image of a whole forebrain organoid taken with scanning electron microscope. The scale bar represents 100 micrometers. View D microscope. View of the forebrain organoid in white sitting on the electrodes of the mirror and the membrane. The hole in the membrane is not visible on the picture since it is hidden by the forebrain organoid. Scale bar represents 500 micrometers. E. Overview of the mirror where the 32 electrodes are visible as 4 sets and 8 electrodes each. And forebrain organoid is placed atop of each set of 8 electrodes, visible as a darker area. For each forebrain organoid, the 2 circles correspond to 2.5 millimeter circular membrane with a central hole. The scale bar represents 1 millimeter. Cross-sectional view of the mirror setup, illustrating the air-liquid interface. The medium covering the forebrain organoid is supplied by the medium chamber through the porous membranes. So to elaborate how this works, the cells are producing electrical activity. They're always producing electrical activity all the time. And with these sensors, you can measure this electrical activity. And so you can stimulate these neurons, and that alters the electrical activity that returns. So you have an input and output. You send in some kind of stimulation, how the stimulation works, that certain aspects of a program might be stimulatory, and the organoid or the neuron or the cell will produce an electrical form. But nobody knows what these things mean. It's all electrical because, everything's an illusion and the brain works on electricity. And so everything that you do gets transferred into electricity. And then the brain turns that into, pictures with your eyes or sound with your ears. A lot of people still think they are looking at reality. They're looking at the real world, but they're not doing that. They're looking at brain stimulations that is producing vision. You're not looking at the real world, you're looking at your brain. That has taken information, turned it into electricity, and then produced a picture. And that's the same thing with all the human senses. It's produced by the brain. It's transferred into electricity and then processed by the brain. So in the same way, we're sending electrical stimulation to these neurons, and these neurons are producing an electrical stimulation. But nobody knows what it means. There's been some efforts, some success with controlling aeroplanes, playing Pong, and doing a bunch of other stuff. Nobody really knows what's going on with this waveforms and this data, and it's a lot of data. A small amount of brain tissue produces a lot of data, a lot of electrical activity. Hardware architecture. 3. Hardware architecture. 3.1 Introduction. The remotely accessible hardware includes all the systems which are required to preserve homeostasis, monitor environmental parameters, and perform electrophysiological experiments. These systems can be controlled interactively using our custom graphical user interface or via Python scripts. All data is stored in a time series database, which can be accessed either via a GUI or via Python scripts. The users typically connect to the system using the remote desktop protocol. Well, I thought it was task scheduling, I didn't think that the user was going to interact with the organoids directly. I thought it would be a task scheduler system where you say, run the Python script and get back to me with the results. But this is a bit different. This is interacting with the neurons directly. The platform is composed of several subsystems which can be accessed remotely via API calls over the internet, typically through Python. 3.2 Multi-Electrode Array MEA. Our current platform features 4 MEAs. The MEAs were designed by Professor Ruslab and described by. Each MEA can accommodate 4 organoids with 8 electrodes per organoid. The MEA setup utilizes an air-liquid interface approach in which the organoids are directly placed on electrodes located atop of a permeable membrane, with the medium flowing beneath this membrane in a 170 microliter chamber. As a result, a thin layer of medium created by surface tension separates the upper side of the organoids from the humidified incubator air. This arrangement is further protected by a lid partially covering the MEA. Figure 1F. The ALI method enables a higher throughput and higher stability compared to submerged approaches, since no dedicated coding is required and it is less prone to have the organoids detaching from the electrodes. This is one of the issues I have, that this isn't the natural environment in which brains functioning. It's kind of an artificial state for them. And I would like to see it move towards a more natural state for the organoids. With 3.3 Electrophysiological Stimulation and Recording System. The electrodes in our system enable both stimulation and recording. The retrospective digital to analog and analog to digital conversions are performed by stimulations are executed using a current controller that ranges from 10 nanoamps to 2.5 milliamps, and recordings are obtained by measuring the voltage on each electrode at a 30 kHz sampling frequency with a 16-bit resolution, giving an accuracy of 0.15 microvolts. The head stages are connected to an Intran RHS controller, which in turn is connected to a computer via a USB port. Figure 2.2 shows the electrical activity recorded for each of the 32 electrodes. It can be noticed that the recorded activity is different between each electrode. The difference comes from the facts that each set of 8 electrodes records a different forebrain organoid, and that for a given forebrain organoid, electrodes record at a different location. This display is refreshed in real time and also available 24/7 on the website at the URL Finalspark Live. We compared the recording characteristics of this ALI setup to MCS MEA, monitoring a submerged forebrain organoid using the exact same Intan system for voltage conversion. The overlays of an action potential recorded respectively with the ALI and submerged versions are shown in figure 2 CD and show similar signal characteristics. 3.4 Microfluidics. To sustain the life of the organoids, on the mirror, neuronal medium, NM, needs to be constantly supplied. Our neuroplatform is equipped with a closed-loop microfluidic system that allows for a 24/7 medium supply. The medium is circulating at a rate of 15 microliters per minute. The medium flow rate is controlled by a BT102J peristaltic pump and is continuously adjusted according to the needs, for instance during experimental runs. The peristaltic pump is connected to the PC control software using an RS-485 interface for programmed, i.e. in Python, or manual operation. Additionally, 3.8 depicts this microfluidic closed-loop circuit. So they're saying that, so it says that under heavy load you pump more fluid. Under light load you pump less fluid. The microfluidic circuit is made of 0.8 millimeter inside diameter, ID, tubing. Continuous monitoring of the microfluidic circuit and flow rate is achieved by using Fluigent flow rate sensors, which connect to the neuroplatform control center via USB. Data related to medium flow rate is stored in a database for later access. Figure 2.8 shows the cyclic variations in flow induced by the cams of the peristaltic pump. A secondary microfluidic system is used to replace the medium in the closed loop with fresh medium every 24 hours, a process illustrated through figure 3.8. This replacement is fully automated through a Python script and performed in the following consecutive step. 1. Set the rotary valve to select the path from the reservoir F50 to the syringe pump. Pump 2 milliliters of old medium using the syringe pump. Set the rotary valve to select the path from the syringe pump to the waste F50. Push 2 milliliters of old medium to the waste using the syringe pump. Set the rotary valve to select the path from the new medium in the F50 in the fridge to the syringe pump. Read out some language that we don't know anything about, but everything works on. Recording system and user interface. Electrical activity measured by microvolts over 1 second for each of the 32 electrodes. Each set of 8 electrodes records a different forebrain organoid. Graphical user interface for manually controlling each of the microfluidic pumps overlays forebrain action. So that's what they want to do, right? They want to say that this is what AI can understand. This is where you have your machine learning, where you have test simulations that create a foundation of what the language could be for machine learning to interpret. Because you could have a lot of sensors, a lot of information, and the only thing that can really deal with that information and sort that information and return something is a machine learning system or one of those LLMs that can do the translation. And AI wants this. AI wants to be in control of the organoids, like the Matrix. You know, it wants that power position. It wants to be the intermediary between the researcher and the organoid, to stimulate and to interpret the results. I think this will be re-engineered at some stage by that. You want to read that. 6. Pump 2 milliliters of fresh medium using the syringe pump. 7. Set rotary valve to select the path from the syringe pump to the reservoir. 58. Push 2 milliliters of fresh medium using the syringe pump. So the AI wants that power position to be the intermediary between the researcher and the organoid, to both do the stimulation, understand stimulation, and understand results, and converse with the researcher in English, in language. Is the AI going to get to that stage, that stimulatory stage? ML doing that? I mean, you need very basic examples where you know the answer. Diagnostic tests that are very basic, and say, okay, maybe something like that would be, colors. Trying to lock down a waveform that is translatable, like a color. Do we see this waveform for a specific color? Yes. That verification, that the stimulation, you're stimulating it with some kind of information, and you're returning, and it returns the waveform, and you're able to recognize that, and you're able to build, this means this means that, this means that. And you would decipher that from real human brains by giving real human brains tests and recording that electrical activity and trying to see, do the organoids exhibit that same waveform? You're trying to isolate a waveform to a stimulation. That is the basis for understanding the language. Basis for building an understanding of the language. 3.5 cameras. Each mirror is equipped with a 12.3 megapixel camera that can be controlled interactively or programmatically, i.e. through a Raspberry Pi, for still image capture or video recording. The camera is positioned below the mirror, where illumination is provided by a remotely controlled LED situated above the mirror. It sounds like these guys are trying to cover all bases for the reason that they want to be organoid intelligence, and therefore they're trying to say, if there's money floating around for this, look, we're doing everything. Like Raspberry Pi, networks. So call us, give us the money. Figures 3b-c illustrate this assembly. The aluminum wrappings is used in order to minimize the noise. This setup is particularly useful for detecting various changes such as cell necrosis, possible organoid displacement caused by microfluidics, variations in medium acidity, using color analysis since our medium contains phenol red, contamination, neuromelanin production, which can happen when uncaging dopamine overflows, where the medium inadvertently fills the chamber above the membrane, or bubbles in the medium. For the latter two events, dedicated algorithms automatically detect these issues and trigger an alert to the on-site operator. Changes of acidity, for example, can be detected by measuring the average color over a predefined window. Figure 2F shows the evolution of the medium's red color component, with data points recorded hourly. The noticeable sudden drop in is attributed to the pumping of medium with a slightly different acidity. This change in acidity results in a color alteration of the phenol red present in the medium. I'm still getting, they're too small, and this is so primitive. I mean, attaching these things to sensors and like they come unstuck. Like, this is so primitive. Like, for this needs to go to a more stable level and a more profound level. You need bigger organoids, more advanced systems. The amount of complexity that this is asking for is unheard of in the history of academia. This is the complexity that this field is asking for is huge. 3.6 UV light controlled uncaging. It is also possible to release molecules at specific timings using a process called uncaging. In this method, a specific wavelength of light is employed to break open a molecular cage that contains a neuroactive molecule such as glutamate, NMDA, or dopamine. A fiber optic of 1500 micrometer core diameter and a numerical aperture of 0.5 is used to direct light in the medium within the mirror chamber. The current system, Prismatic's silver LED, operates at 365 nanometer with an optical power of 260 milliwatts. The uncaging system is fully integrated into the neuroplatform, quotation marks, and can be programmatically controlled during experiment runs via our API. So this idea of the neural platform, this is the whole package. This does everything in OI. You know, it is called, this is the neural platform. It does everything. It's a complete system for OI. 3.7 Environmental measurements. The environmental conditions are monitored within two incubators. In both incubators, the following parameters are recorded: CO2, O2, concentrations, humidity, atmospheric pressure, and temperature. Door opening events are also logged since they have a major impact on measurements. The primary purpose of this monitoring is to ensure that experiments are performed in stable and reproducible environmental conditions. All these parameters are displayed in real time in a graphic interface showing both instant values as well as variations versus time of noise and flow rates, figure 4.8. So if somebody was to come and say, okay, you know, you guys are last year, we're going to build a system that's twice as good as yours. We're going to build the neuro system version 2, and it's going to make your neuro platform look like a steam engine. Like, it would have to, like, you would take this manual and say, okay, what are those guys doing? You know, well, we're going to have to improve on that. We're going to have to build a better one than that, you know, because this is pretty comprehensive. Incubator 1 houses the mirrors and the organoids used for electrophysiological experiments. In addition to the mentioned parameters, flow meters are also utilized to report the actual flow rate of the microfluidic for each mirror, as depicted in the graph labeled pump in figure 4.8. The system state is indirectly monitored through the noise level of each mirror, as shown in the graph labeled noise in tan in figure 4.8. The noise level is calculated based on the standard deviation of the electrical signals recorded by the electrodes over a 30 millisecond period. Incubator 2 houses the organoids, which are kept in orbital shakers. Piezoelectric gyroscopes are used to measure the actual rotation speed of the orbital shakers. Since all data is logged in the database, it is also possible to access the historical measurements through a dedicated GUI, figure 4.b. So you would have to double everything, right? You have to put Moore's law on it, and you know, everything has to be 2x'd, you know. All the systems have to be 2x'd. 4. Software 4.1 General Architecture. The core of the system relies on a computational notebook which provides access to 3 resources, figure 4.8. A database where all the information regarding the Neuroplatform system is stored, the intense software running on a dedicated PC, which is used for recording the number of dedicated spikes in a 200 millisecond time window, setting stimulation parameters. A Raspberry Pi for triggering current stimulation according to stimulation parameters. So the neuron is stimulated and then it returns some deviated electrical activity. The stimulation can be either electrical or chemical. So in reinforcement learning, when the neurons are doing what you want, you hit them with dopamine. The neurons are trying to control an aeroplane and keep it horizontal, across the 3 axis. So it's and there's the wind trying to change its pitch, and you're noticing those little fluctuations, and as you notice that it's done the right thing, you're hitting it with dopamine, and so it says, oh yeah, this is the right thing, this is the right, until it learns what the stimulation wants, which is keep the plane level. 4.2, the database. The Neuroplatform records monitored data 24/7 using InfluxDB, a database designed for time series. Other options are also available. The database contains all the data coming from the hardware listed in section 3. The electrical activity of the neurons is also recorded 24/7 at a sampling rate of 30 kHz. To minimize the volume of stored data, we designed a dedicated process that focuses on significant events such as threshold crossings that are likely to be due to action potentials, spikes. Following pseudocode illustrates the implemented approach. Each 1mm write buffer to the database, each 33 microseconds. Each 1 minute write buffer to database, each 33 microseconds. For each electrode, if at time t the voltage exceeds the threshold t, store in buffer 3 milliseconds of data t, 1 millisecond t plus 2 milliseconds, each 3 second update t. Additionally, a timestamp corresponding to each detected event is also stored in the database along with the maximum value of voltage during a 3 millisecond spike waveform recording. So this would then say that there is no language, that the language is the language that you set, and that is reinforcement learning. Oh, I like what you've done, here's a drug, and so do it again. And as the task becomes more complex, you're developing the intelligence for your specific application. The medium flow system of medium going out and new medium coming in, flow meter. Okay, figure 3, microfluidic system illustrating the continuously operating primary system which ensures constant flow in the medium chamber, and the secondary system responsible for medium replacing every 48 hours. Some view of the assembly featuring the camera and the mirror. The entire assembly is enclosed with an aluminum foil to ensure the lowest possible noise level. Front view of the assembly showing the intake and outtake of the microfluidic system, as well as LED used during image capture. If you were to assign a waveform an English language, and you would use reinforcement learning to say, oh, well, that means that, and that means that, and that means that, because that's what feels good when you do that. So everything becomes arbitrarily re-encodable. But Not at that stage, because if you're thinking about LLMs and can these things then can those waveforms be encoded into language and say, well, I said hello to you and, you did not say hello back, so no drug for you. I guess what you want to do is try and sample human language from a real brain, or try and sample some revealing encoding from a real brain, and then try and represent that in the organoid. So if you read some poem, coupling that with the organoid and trying to create some similarity between the two waveforms, the threshold T is computed directly from voltage values sampled each 33 microseconds according to the following formula. T equals 6 times MDN sigma I, where sigma I is standard deviation computed over a set I of 30 milliseconds, consecutive voltage values, and MDN represents the median function computed over 101 consecutive sigma subscript I values. The use of the median reproduces the sensitivity of two outliers, which is typically caused by action potentials. In our current setup, a multiplier of 6 on the median has proven to be a good compromise for achieving reliable spike detection. Besides electric tension data, the number spikes recorded per minute is also computed and stored in the database every minute by a batch process. Graphic user interface to monitor the critical parameters in the incubators. A graphical user interface displaying the critical environmental conditions for incubator 1, where electrophysical experiments are performed, as well as incubator 2, where forebrain organoids are maintained on an orbital shaker. B, the display shows environmental data for the incubator 1 for specific time periods extracted from the database, with door opening events displayed as dashed line. Noise, temperature, humidity, and pressure are indicated by different colored lines. The units of each measurement are normalized between 0 and 1 for the select time interval. 4.3 Recording electrical activity. As previously discussed, the communication among neurons is captured by the mirror and converted into a voltage signal sampled at 30 kHz. The neural platform offers two basic access modes to the recorded neural activity. 1. Raw sampling values. 2. Optimized waveforms of raw signal near neural spikes available directly from the database. In addition to the aforementioned features, the neural platform offers even more advanced method. For instance, it includes counting spikes over a fixed time period of 200 milliseconds following stimulation, with a 10 millisecond delay, suppressing the stimulation artifact. From technical perspective, accessing the number of spikes can be accomplished in two different ways: retrieving the number of spikes per minute from the database through direct communication with PC, managing the intent controller for spike count. The second approach is required when the stimulation protocol demands real-time responsiveness. This is typically the case for certain closed-loop strategies. For instance, closed-loop stimulation strategies have been deployed in primary cortical cultures for effective burst control for goal-directed learning. So, this is a subject, this is a degree on its own. This is somebody coming into this field and determining how the next level is played out. Because there's no shortage of complexity that requires intelligence to solve, to make this system more viable. 4.4 Syntax for Stimulation. Programmatically stimulating the forebrain organoids on the neuroplatform is accomplished by sending an electrical current to the mirror electrodes. The electrical current profile can be parameterized in a variety of ways, which is partly shown in Figure 5.b. These parameters and controls include basic shape of stimulation signal, biphasic with interphase delay, triphasic. Stimulation duration and intensity, positive A1 and negative A2 electrical current intensity, typically 1 microamp, ranging from 0.1 microamp to 20 microamp. Duration of positive D1 and negative D2 stimulation currents. Stimulation triggers, single start, table with collection of start triggers, pulse trains, MEA electrodes, send stim param electrodes, param. So what is this stimulation? So software setup and electrical stimulation. General architecture of the neuroplatform. The Jupyter Notebook serves as the main controller, enabling initiation and reading of spikes, configuration, stimulation signals, and access to the database, Python. So database, Intran software, trigger generator, Intran, head stage, incubator. B, parameters of the stimulation current settings optimally. These parameters can elicit spikes. Through the Python API, parameters can be adjusted for biphasic stimulation signals, include the duration D1, the amplitude A1, and the positive current phase, and respectively D2 and A2 for the negative current phase. Additionally, the polarity of the biphasic signal can be reversed to start with a negative current. Amplitude 1, duration. Amplitude, duration of an electrical signal to elicit a spike in the neuron. But what is it encoding? What is the language? Assume that it doesn't know anything and that it's going to learn, it's going to undergo learning, and that is, the learning is based upon recognition, positive reinforcement. And from that device, that mechanism, that system, you can develop a language from that. A language which the neuron learns and which the operator also knows, perhaps. So there is no set language. It has to assume that it has to learn the behavior, the language devised. Now, this is the Organoid Intelligence Language Manual. This is how you train it in the language. 5. Examples of electrophysiological experiments. To demonstrate the effectiveness of neuroplatform, the following sections will provide an overview of several experiments conducted on the neuroplatform at Finalspark's laboratory in Vevey, Switzerland. 5.1 Modification of spontaneous activity. The spontaneous electrical activity of the forebrain organoid can be represented by the concept of center of activity, CA, which is defined as a visual position C on the mirror described by formula, where X subscript K, Y subscript K define the spatial position of the 8 electrodes, and F subscript K is the number of spontaneous spikes detected. The interest of the concept of center of activity is that its position provides statistical information about the average location of the activity over the surface of the forebrain organoid. The ability to change the position of the center of activity is interesting because it also shows the ability to memorize information in the state of the forebrain organoid. The coordinates of the center of activity can be modified using high-frequency stimulation. In the following experiments, we use the following protocol. Compute the center of activity using a number of detected spikes over 500 milliseconds. Go to 100x. Perform a 20 Hz stimulation during 500 milliseconds using a biphasic current, negative first of 2 microamps of 200 for both phases on one electrode. Well, it's amplitude duration. Wait 1 second. Go to 100x. Figure 6a displays the 100 measured positions of a center of activity corresponding to the spontaneous activity before the 20 Hz stimulation in blue and after the high frequency stimulation in red. The average position is indicated by a cross. A close-up is shown in figure 6b. The timestamps of the spontaneous activity before and after simulation are presented in figure 6cd respectively. Each graph shows one example of the 100 records of 500 milliseconds used to compute the center of activity location, showing a decrease of spontaneous firing activity of electrodes 3, 4, and 6. A noticeable shift in the average position shown by a cross of the center of activity can be observed before and after the high frequency stimulation as seen in figure 6.8, indicating a change of state of the biological network. A classifier based on a simple logistic regression is employed to predict if the network has received 20 Hz stimulation. In this particular experiment, the classification accuracy computed from the confusion matrix is 95.5%. The neural platform allows users to perform both the experimental part, including stimulation and reading operations, and the visualization of the center of activity displacement within the same Python source code. The 500 milliseconds 20 Hz signal is generated directly by the Python source code shown below. The first trigger.send instruction sends the trigger for the stimulation of a specific electrode and time, sleep pauses, and execution of 50 milliseconds. For I in the range of 20, trigger send, reading triggers, time sleep. So it's triggering stimulation on a specific electrode and time. The time is the 0.05 and the trigger send is, well, it's in the range of 1 to 20, with I being variable, so it's changing where it's triggering. It's changing the electrode, so it's incrementing the electrode each time, which electrode it's stimulating, and it's sleeping for the 50 milliseconds, which means it's doing it every 50 milliseconds. Despite the common perception of Python as being less than ideal for real-time signal processing due to the inherent latency, our empirical data reveals a time accuracy of under 1 millisecond. On an Intel Xeon CPU ES2690 version 2.3 GHz, a level of precision that is satisfactory for the generation of tectonic signals. 5.2 Optimization of stimulation parameters. In this example, the objective is to identify the set of stimulation parameters that can elicit the maximum number of action potentials within 200 milliseconds after the stimulation. Depending on the forebrain organoids, their composition and maturity, only specific combinations of electrodes and parameters can elicit spikes. In our experiment, we use an 8-electrode mirror and cycle through several stimulation signal parameters as shown in Figure 7a. Consequently, we need to test a total of 342 different parameter electrode combinations. The following pseudocode illustrates the Python script used in this experiment. 1 for each set of stimulation parameters, 2 for each stimulation electrode, 3 for each recording electrodes, duration 15 seconds every 250 milliseconds. Decide between stimulating or recording spontaneous activity with a 50% probability, random. 6 record number of spikes during that 200 milliseconds. The aim of the probabilistic stimulation and no stimulation in step 5 is to evaluate the difference between illicit and spontaneous spikes in a way that ensures there is no bias. The bar chart in 7a displays a segment of the experimental results. It shows a 15-second recording from a single electrode corresponding to one execution of step 4 in the pseudocode above. Each bar represents the spike count during a 200 millisecond period, repeated every 250 milliseconds. The orange bar in the plot as a result of the parameters selected in step 1 of the pseudocode. The blue bars represent no stimulation periods, thus corresponding to the spontaneous activity of neurons. I would say that this is all very dated. That how much of this is going to survive development? If Organoid Intelligence undergoes development, how much of this information is going to be valid? That this is the way that they have done it, that they used to do it. Figure 6, Center of Activity Modification, a graph showing the 2D layout of the 8 electrodes X and Y, a normalized unit showing the spatial coordinates of the electrodes. All electrodes can be used for both stimulation and reading. A 20 Hz stimulation signal is applied to electrode 6. The 100 blue circles represent the positions of the center of activity before 20 MHz stimulation, while the 100 red circles indicate the positions after the stimulation. The cross mark is an average position. Closer look at the two groups of center of activity, timestamp C. Center of activity C, timestamps depicting the spontaneous activity over 500 milliseconds for each of the 8 electrodes before the high frequency stimulation. D, spontaneous activity observed after the high frequency stimulation, showing a lower activity of electrodes 6, 4, 3 compared to C. From figure 7a, we can see that this particular combination of electrode and parameters reliably elicits responses. In practice, the Python script can also be used to automatically display the 342 graph similar to 7a, allowing the operator to select the optimal set of parameters. Additionally, it can compute a scalar metric to characterize the efficiency of the parameters and automatically identify the optimal parameters. An example of a parameter maximization metric is given in the equation below. Let us denote x subscript r and x subscript s, the average number of spikes recorded spontaneously or after a stimulation, respectively subscript r and subscript s as their standard deviation. The following metric is used. The set of parameters that maximize this metric can then be utilized to perform other experiments requiring elicited spikes, such as investigating the effect of pharmacological agents on a biological network's ability to react quickly to stimulation. 5.3 UV light-induced uncaging of molecules. Uncaging is a pivotal technique of cellular biology, enabling the precise control of molecular interactions within cells. It involves the use of photolabile caged compounds that are activated by specific light wavelengths, releasing bioactive molecules in a targeted and timely manner. This method is particularly valuable for studying dynamic processes in neural network and intercellular signaling, offering real-time insights into complex biological mechanisms. Our neuroplatform is equipped with all necessary components to perform uncaging. In this example, we investigate closed-loop stimulation where dopamine is used to reward the network when more spikes are elicited by the same stimulation. The response of the dopamine is achieved through the uncaging of CNV dopamine using the UV system described in section 3.6. Figure 7b shows the flowchart of the closed-loop uncaging process. The optimal stimulation parameters are first found using the technique shown in 5.2. In this case, a current of 4 microamps biphasic with 100 microsecond per phase, with 100 microsignal per phase, which is sent successively to each of the 8 electrodes with a delay of 10 milliseconds between each electrode. Figure 7.c shows the response timestamp of the 8 electrodes for a period of 1,200 milliseconds, 600 milliseconds before and after stimulation. The stimulation event is indicated by the vertical red line. It is interesting to observe that in this particular case, most of the elicited spikes originate from 2 electrodes, specifically electrode 112 and 119. The Python source code implementing the closed-loop process illustrated in Figure 7b is provided below. We would like to highlight here how concise the code was. With only 13 lines of code, the entire closed-loop process had been implemented. So this neuron's always making noise, and then it can spike randomly. They're trying to create a surety of spike to stimulation, a spike to stimulation. The graph in Figure 7.d shows the variation in the number of spikes elicited during the execution of the script above across 5 hours. A general increase in the size of the elicited spikes can be observed. However, it is obviously not possible to establish causality between the closed-loop strategy and the observed increase with this single experiment alone. The primary purpose of this closed-loop experiment is to demonstrate the flexibility offered by the neural platform. 6. External uses of the neuro platform. Access to the neuro platform is freely available for research purposes. For research lacking lab infrastructure, the neuro platform provides the capability to conduct real-time experiments on biological networks. Additionally, it allows others to replicate results obtained in their own lab. The database is shared between all research groups. However, the Python scripts and Jupyter notebooks are in private sections. In 2023, 36 academic groups proposed research projects, of which 8 were selected. At the time of writing, 4 of these have already yielded some results. Being used investigates the functional connectivity of forebrain organoids and how electrical stimulation can modify it. Investigates stimulation protocols that induce global changes in electrical activity, like how basic is that? Investigates stimulation protocols that induce changes in electrical activity of a forebrain organoid. Additionally, this research employs machine learning tools to extract information from neural firing patterns and develop well-conditioned responses. Moreover, it utilizes both shallow and deep reinforcement learning techniques to identify optimal training strategies aiming to elicit reproducible behaviors in forebrain organoids. So, you have an LLM that is training to read the neurons. However, you're going to, there's a lot of data, there's a lot of training data, but read these neurons and determine some pattern into understanding what the hell is going on. Investigate storing and retrieving of spatial temporal spiking patterns, use closed-loop experiments that combine mathematical models of synaptic communication with the neuroplatform, characterizes computational properties of forebrain organoids under the reservoir computing model with a view to building low-power environmental sensors. So that's interesting. So most groups are just trying to work out, let's send it a signal and see what we get back from this signal, and then let's send a stimulation and see what returns, and then give that a fancy name, and then because it's such at a basic level. I mean, these people are interesting. They want to see if they can turn it into some kind of a device that is able to sense something as a sensor. Can a organoid be a sensor? Investigating the properties of emerging dynamics and criticality within neural organizations using forebrain organoids. Using the free energy principle and active inference to study the learning capability of neurons embodied in a virtual environment. Stimulating of forebrain organoids based on data gathered from an artificial tactile sensor. Use machine learning techniques to interpret the forebrain organoids' output, investigating their ability to process real-world data. They could be making noise all the time, with the valuable noise being these spikes, or they could be producing valuable information all the time, but it's just too much information and too complex to know what it is. Seven, discussion and conclusion. The neural platform has now been operational 24/7 for the past 4 years. During this time, the organoids on the MIA have been replaced over 250 times, considering that we place at least 4 organoids per MIA and change all the organoids simultaneously. This amounts to testing over 1,000 organoids. Initially, their lifespan was only a few hours, but various improvements, especially related to the microfluidics setup, have extended this to up to 100 days in best cases. It is important to note that the spontaneous activity of the organoids can vary over their lifetime, a factor that must be taken into consideration when conducting experiments. Additionally, we observe that the minimum current required to elicit spikes, computed using the method described in section 5.2, is increasing over the lifetime of the organoid. This phenomenon may be linked to an impedance increase caused by glial encapsulation. The 24/7 recording strategy, as described in section 4.2, results in the constant growth of the database. As of this writing, its size has reached 18 terabytes. The volume encompasses the recording of over 20 million individual action potentials, each sampled at 30 kHz resolution for 3 milliseconds. The extensive dataset is significant not only due to its size, but also because it was all recorded in a similar in vitro environment as described in section 2. We are eager to share this data with any interested research group. I mean, that's what large language models thrive on. Huge amounts of data, but not just any data. The data must represent something, but it must represent something so many times, hundreds of thousands of times, for the network to learn. But the fact that these organoids are producing so much information is good, could be beneficial in terms of training an artificial network to interface with the neuron. 8. Future extensions. In the future, we plan to extend the capabilities of our platform to manage a broader range of experimental protocols relevant to wetware computing. Whoa! Neural Platform 2. Gauntlet's out. They're not going to rest on Neural Platform 1 and wait for some other group to double everything, double the size of them, double the lifespan of them, just completely revolutionize this and say, look guys, you had Neural Platform, look at our system. No. These guys are already working on Neural Platform 2. For example, we aim to enable a remote control over the injection of specific molecules into the medium, facilitating remote experiments that involve pharmacological manipulation of neuronal activity. This expansion will provide additional degrees of freedom for the automatic optimization of parameters influencing neuroplasticity. Currently, as detailed in Chapter 2, only one differentiation protocol is used for generating organoids. We plan to introduce additional types of organoid generation protocols soon, with the aim of exploring a broader range of possibilities. Although 32 research groups requested to access to the Neural Platform, our current infrastructure only allows us to accommodate 7 groups, considering our own research needs as well. We are in the process of scaling up the AC/DC hardware system to support more users simultaneously. Additionally, we are currently limited to executing closed-loop algorithms for neuroplasticity on one single 4-brain organoid, as these algorithms require sending in real-time adaptive simulation signals to each 4-brain organoid. Our software has been updated to run closed loops in parallel on up to 32 4-brain organoids. 9. Methods. 9.1. Brain organoid generation. This information is fantastic for those who want to make organoids. 9.2. Electron microscopy analysis of 4-brain organoids. Electron microscope scanning, transfer of 4-brain organoids on the mirror. This is all the architecture. 9.4 system, 9.4 system design and assembly. Great work. Uncaging of dopamine. And so they even share some inside data on how to construct organoids. And there are all the references. So there it is. Finalspark's neural platform. Open and remotely accessible neural platform for research in wetware computing. Now they've got a system. It's a comprehensive system. It's a primitive system. They're working on a version 2 of the system. But there is a lot to do. There is a lot of advancement to be done in all aspects of maintaining these neurons for 100 years and the systems that will maintain these neurons for 100 years. The information, the communication, the scalability, the size of them. All of this stuff has to be worked out. Who's going to work it out? Okay, guys. Tony, over and out.